All right, press record. So we're now recording. So if you don't want your video recording, you can turn off your camera. Min Sue, I got you. Okay, now. See what it gets set up here, sorry. Okay, I'm going to try to share the screen. All right. Okay, first order of business, I will finish 13.4 today. In fact, it's not really that long a section, which means I will have already finished everything we need to for the next exam, which means theoretically I could have given you the test next Tuesday, but I'm not going to do that. I'll keep the date originally here. I'll just go on and get ahead and start with chapter 14. Okay, so we're here, 13.4. It's a fairly simple section. Okay, and I'll probably sneak in some of 14.1. So next exam is going to be on the 23rd. I won't change that. Okay, I should finish today. So I'll just start getting 14.1, 14.2. We'll see how we go. And how about let's make it Thursday of next week. I'll give you some time for question and answer. So if you have any questions from chapter 13, that'll be fine. And then even on the day of the test, Tuesday, I'll lecture, quote unquote, a while. Okay? And same thing, I'll let you ask questions. And then if that stops, we can start the test early. Okay. Now, just give you a heads up. I'm leaning toward for exams 3, 4, and 5 to let you have the entire class period for that. They're just longer. Some of the problems just take that much time. Like the last time I taught the course, I gave the class 2 hours for the exam, so we may need that when time comes. Okay. Looking a little bit ahead, Tuesday, March the 2nd is a flex day while we don't meet on that day. Okay. Okay, next order of business, and I'm not sure if you were part of this or not, but I got this thing here. We'll see if it makes a difference. Okay. In fact, I got this in the mail, and I'm not sure if you were part of it, but I'll show it to you anyway. This is what it says. From your CCSF math classes. Okay, now I don't know if that accounts to you folks, or some of them, maybe you have absolutely no idea how that happened. It may have been last semester. It'd be kind of interesting if it were you folks because the semester just started. But whoever gave it, thank you. If you were part of it, I thank you very much. If you have no idea where it came from, maybe it was my last semester, I don't know. I guess you don't have to tell me if you don't want to, but if you want to tell me that you folks were part of it, that's fine, that's great. But I'm going to try it out for the first time. Okay, so maybe this will take care of issues. And I may ask some of you to tell me if it's better or worse. As I tried this thing, I'm not very good at this. In fact, when I put this on, I kind of feel like I'm like a travel agent or something, or somebody who's answering the telephone. I don't feel like a teacher with all that. Okay, so I'm going to give this a shot and plug this thing in. I might even ask some of you for help. Okay, testing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can some of you maybe give me a comment on whether you think it's better or worse, or worse, better, way better, quality is good? I mean, okay, all right, great. Quality is better, definitely better. Okay, great.
Sounds much better.
So I'll use this.
Sounds
Except a weird thing is, I'm too loud myself, so I kind of hear myself as an echo. So let me turn my volume down. Where go this? I don't think it affects you guys. All right, so maybe that'll help. And I think the recordings, you guys were getting a buzz, right? While I was listening to myself, it was kind of zzz or something like that. So maybe that takes care of that, which kind of makes sense because instead of talking over the air, right, going through the air molecules and all that, that it's going directly into the computer through this thing. Oh, I guess I got to, you can kind of tell I'm not very good at this. Turn this up like so. I think that's how it works.
I obviously have no experience with this. So, all right, so most of you are saying no crackling, sound better. Okay, good. So, yay, it works. So if you were part of this, I thank you. If you were not part of it, thank you anyway, I guess. But somebody gave it to me. There was no names attached to it except for this is exactly what I got from your CCSF math classes. So if it's not you folks, then great, you don't have to pay for it and you get the benefit, you get to reap the benefits of it, I guess. So thank you one way or the other. Okay, so, all right, so let me get started. So yeah, I hear myself a lot too, so hope I don't go deaf by talking to myself doing this. But anyway, right, so all we have left for this upcoming test is 13.4. And now I've got wires all over the place too. I have to make sure I don't trip all over all this stuff. And I can't really go as far, because I'm tied down to this unless I take this off. All right, so 13.4. So motion in space, velocity and acceleration. And a lot of this really just mimics what happened in Calc 1. Okay, pretty much what you had before. Here's a very formal definition of velocity. You don't even have to write it down. There are no homework problems involving it, but it looks like the definition of derivative, right? Limit h approaches 0 of r of t plus h minus r of t all over h is r prime of t. Okay, tangent. Move along the tangent. How do you get the tangent? You move off a little bit, r of t, move off a very tiny h, r of t plus h, okay, and find the slope of that secant, so to speak, okay, and then let h approach 0. Okay, don't even bother writing that down. There are no homework problems involving that. I really hear myself loudly. I don't know if there's a way to do that. By the way, if I obviously don't know as much as some of you, so if you know how to make it so I don't hear myself buzz all the time, then let me know. But anyway. Okay, so what do you really need to know? Something that you already know. Oh yeah, let me move this over again. Sorry. So what happened in Calc 1? Velocity was the first derivative. Acceleration is the second derivative. It's the exact same thing, only we're in 3 dimensions. Okay, so here is a 2-dimensional picture. Velocity, acceleration. Acceleration, as you may know, is proportional to force. Force F equals ma, a lot of you know that. Okay, so this can be thought of as a force, and that's a velocity vector right here. Okay, but velocity, first derivative, acceleration, second derivative. So if they give you a distance, I was going to say distance function, or position function more accurately, either in 2 dimensions, I and j, or 3 dimensions, I, j, k. Okay, the first derivative is the velocity vector v. Second derivative is acceleration. Okay, very simple example. Example 2 on page 871. Okay, so they give you the original r. Got to put the book down. Okay. Again, we're going to say take the derivative, but when we say take the derivative, you're really taking 3 derivatives, right? So r prime is the velocity vector. Second derivative, acceleration vector. Okay, and there's the picture in 3D. Okay, so at a particular point in time, there's a velocity vector, there's the acceleration vector. Okay, you can put that in your cheat sheet, but I don't think you really need to. I think you've heard of that all before. Okay, now what is this? This is speed. Okay, speed is the magnitude of the velocity vector. Okay, velocity is a vector. Okay, so 40 miles an hour that way, or 60 miles an hour that way, or 100 miles an hour that way. Not so for speed. Speed does not have any direction, so therefore it's just a magnitude of the velocity. Now, in 1 dimension, if you just have a number line, right, then you either have a positive or a negative value, right? So if you're moving to the right, you say, okay, 50 miles an hour. If you're going to the left, you say negative 50 miles an hour, but your speed would be absolute value, right? 50 miles an hour. So same thing, the analogy for absolute value is magnitude, okay? So for the speed, here we go, speed is just the magnitude of the velocity vector, okay? And if you want to put that in your formula sheet, you may, okay? Maybe just right over here. Where'd it go? I lost it, but yeah, speed is right here. So magnitude of the velocity vector is the speed. I'll show you examples of that too. So look at example 2. Find velocity, acceleration, and speed. So example 2. So velocity, first derivative. Acceleration, second derivative. Speed is the magnitude of the velocity vector. Okay, so they did square root of 2t squared plus e to the t squared plus all of that thing squared. Okay, so that's considered the speed. Okay, and this is a scalar quantity. It's not a vector. Okay, just take the magnitude of the velocity vector. Okay, and that's the way that works. Okay. The only extra thing that's new, and there's only, I think, 2 homework problems involving it. Tangential and normal components of acceleration. Okay, so here's the picture. You don't even have to put down this picture, but the idea is, okay, you have an acceleration vector, right? And that could be proportional to force. F is equal to ma from physics. So this could be thought of as a force. Okay, you might want the tangential component. Okay, what's the magnitude of the force going this way? And what's the magnitude of the force in a normal direction? Okay, and here are formulas for those. Formulas 9 and 10 on page 875. Put these on your formula sheet. A sub t is a tangential component of acceleration. Number 10, a sub n is a normal component. Okay, the only thing you really need to put down are that one and that one. They look very similar. Okay, number 9 involves a dot product. Number 10 involves a magnitude of a cross product, and the denominators are the same. Okay, so for number 9, the numerator is r prime dot r double prime, dot product over magnitude of r prime, speed. And 10 is magnitude of the cross product. But otherwise, if you look at 9 and 10, they look like the same formula. The bottom's the same, it's a speed, magnitude of r prime. For number 9, a sub t is a dot product, r prime dot r double prime. Number 10 is the magnitude of r prime cross r double prime. Now remember, a dot product is already a scalar. Cross product is a vector, so that's why you put the magnitude. It looks like absolute value again, but since it's a vector, you're taking the magnitude of the cross product. Okay, so there we go. Okay, don't worry about the Kepler's laws. We don't have any homework problems involving it. You can look at it for those of you in physics or astronomy. Kepler's laws of planetary motion, they're true and they're nice, but since you don't have any homework problems involving it, we'll just go straight to the homework. Okay, so let me get to the homework, but I do see some stuff in the chat. Let me see what it is. It might have to do with this thing also. So let's see. Okay, Windows, okay, I'll have to look at that later. Something about filter. Oh, say something about a cat filter. All right. All right. So we'll see how that goes. Okay. So we'll go ahead and get started, except I'm hearing myself a lot. I don't know how to fix that, but yeah, if anybody has any suggestions, please let me know. And by the way, you might be saying some stuff that I don't even know what you're talking about. I'm very naive when it comes to stuff like that. Basically, I'm not that smart, okay? So I can maybe do a little bit of math and that's about it. All right, so 13.4. 3 through 19, 37, and 39. And unfortunately, I forgot to have my watch or cell phone here, so I have to look at my wall clock. Can't even tell what time is it, but is it about 6:30-ish now? Okay, so we'll see. All right, so the first problems. Okay, Okay, 3 through 8. Find the velocity, first derivative, acceleration, second derivative, and speed, magnitude of the velocity of a particle with a given position function. Sketch the path of the particle and draw the velocity and acceleration vectors for the specified value of t. Now, the two-dimensional ones you should be okay with, okay? And I only give you quote unquote easy 3D ones, okay? So I'm not making you be experts on graphing three-dimensional stuff because I'm not, okay? But you should be able to just do elementary stuff. Two-dimensional ones, hopefully not too bad. Okay, so I'll do number 3 for you. And I'll do number 7 since it's a three-dimensional one also. Okay. So number 3, R of t is -1/2 t squared t. Okay, and they're talking about at t equals 2. Okay, so first I want to declare what the point is. Okay, and you know, what's the point? Haha, not what's the ordered pair or ordered triple? You guys know what I mean. Okay, so I plug in 2. So plug in 2, -1/2 times 4 is -2 and 2. Okay, so the point is -2, 2. I'm in 2 space. See, how do you know you're in 2 space? Well, you can look here. There's only 2 components, right? Number 7, you know you're in 3 space because there's 3 components, right? I, J, K. This one's just I and J. All right, so R prime, velocity, first derivative. That's easy. So derivative of that is -t. Derivative of that is 1. Now plug in t equals 2. Put a 2 there. There's nothing to plug in there. So the velocity vector is -2, 1, or -2i plus j. Acceleration vector, second derivative. So the derivative of -t is -1. Derivative of 1 is 0. Okay, and that's equal to, should be a -i. Sorry, -i. So in 2 dimensions, the regular x and y coordinate, the force, as it were, the force is -i. It's going to the left. So imagine pulling directly to the left here, and there's the acceleration vector. Okay. Speed is magnitude of the velocity vector. So it's the square root of -t squared, which is t squared, plus 1 squared, or square root of t squared plus 1. And what's the speed at t equals 1? I just plug in radical 2. So the speed is radical 2. Notice it's a scalar. So you have a velocity vector, magnitude and direction. The speed is only the magnitude, radical 2. Okay, so here's the picture. Okay, now I put x equals -1/2 y squared. How did I get that? Well, I got that from over here. Okay, t is the same as y. So it's y equals -1/2 t squared, or x equals -1/2 y squared. So it ends up looking something like this. Okay, in other words, just put t is y, right? So just put a y here. X is -1/2 y squared. It's a parabola opening to the left. Okay, so the velocity vector, they said, was -2, 1. So very crudely, something like that. And that kind of looks like a tangent, right? It's going off at a tangent. The speed is its magnitude, which is radical 2 at that particular point. The acceleration vector is 1 unit to the left. Imagine you're pulling it in that direction. And there you go. Okay. All right, 7 is a 3-dimensional version. Yeah, I want you to give some attempt at some quote unquote easier 3-dimensional pictures. All right, so R of t is t squared 2 at t equals 1. Okay, so same thing. It's asked for velocity, acceleration, speed, and draw the picture. Okay, oh, by the way, this is R. R is the position vector. You should have put this. R is position vector, position vector. The position vector always starts at the origin. Comes from origin. Position vector comes from the origin. Okay. So plug in 1, 1, 1, 2. So the point is 1, 1, 2 in in 3 space. The position vector is 1, 1, 2. So please distinguish. I know it's easy to mix these up. The position vector is 1, 1, 2 with the angle braces. The point ordered triple is 1, 1, 2 as a point in space. The position vector, which emanates from the origin, is also 1, 1, 2, but you write it with the braces. It's a vector. All right, so that's easy. R prime, the velocity, derivative of t is 1, derivative of t squared is 2t, derivative of 2 is 0. And second derivative, let's see. Oh, first R prime of 1, right? So I plug in 1, 1, 2, 0. Or you can say I plus 2j. So that's the velocity vector at time t equals 1. Okay, acceleration, second derivative. So derivative of 1 is 0, derivative of 2t is 2, derivative of 0 is 0. Okay, so the acceleration vector is 2j. So it's 2 units to the right. Remember, in 3 space, x, y, and z is like that. So the acceleration vector, which is proportional to the force vector, so the force vector is pulling directly to the right in this particular case. And speed. Speed is the magnitude of the velocity vector. So square root of 1 squared plus 2t squared, 4t squared, plus nothing. I messed up there. What's new? So radical 1 plus 4t squared. And right at t equals 1, what's the speed? So I plug in 1, radical 5. All right, so what did I do here? Very feeble first octant picture. Okay, so I try to plot the point 1, 1, 2. So I went 1, 1, 2, like so. Okay, so this vector right here is r, starts at the origin, goes here. The vector v was 1, whoops, where'd it go? 1, 2, 0. Well, at least the z component is 0. So I'm not going up or down. So this is supposed to represent 1 unit out and 2 to the right. And this is the acceleration vector, which is just 2 units to the right. That's all. Okay, so again, our position vector always starts at the origin. Okay, and that's supposed to mimic 1, 1, 2. So 1 out, 1 right, 2 up. And fortunately, both of these z components are 0, which means you're not going up or down. So 1, 2, 0. Okay, I go out 1, 2 over. So this is the vector v, and that's the vector a. Okay, so that's all. All right. Okay, then 11. No more drawing at least. Find the velocity, acceleration, and speed. Very easy, right? First derivative, second derivative, and then magnitude of the velocity for the speed. Okay, no drawings. So that should be fairly straightforward, right? 9, 11, 13. So I will show you 11. Radical 2t, e to the t, e to the negative t. Okay, so first derivative, r prime, is the velocity. Derivative of that is radical 2. Derivative of e to the t is itself. Derivative of e to the negative t is negative e to the negative t. Okay. Second derivative is the acceleration, a. Derivative of radical 2 is 0. Derivative of e to the t is itself. The derivative of negative e to the negative t, again, becomes positive e to the negative t, right, by the chain rule. And then the speed, and Mr. Stewart likes this theme quite a bit. Okay, so it's the magnitude of the velocity vector. So it's radical 2 squared, 2, e to the t squared, e to the 2t. Negative e to the negative t quantity squared is a positive e to the negative 2t. Okay, and it turns out that this thing is a perfect square. This thing is e to the t plus e to the negative t quantity squared. You can multiply it back off to check. Okay, that's like a plus b squared. Okay, so I square this, e to the t squared, that. Square this, e to the negative t squared is that. And then what about the middle term, the 2ab term, plus 2 times a times b? What's e to the t times e to the negative t? Well, we're supposed to add the exponents. That's e to the 0, which is 1. So it's just 2. So you have the square root of a square. So the answer for the speed is e to the t plus e to the negative t. Okay. So that's basically it. Okay, and let's see, 15. Find the velocity and position vectors of a particle that is given acceleration and a given initial velocity and position. Okay, so 15, they give you the acceleration vector and they tell you something about the velocity and the position r. Okay, so this is like, remember when they give you the second derivative, you integrate to get the first derivative, then you integrate again to get back the original f, right? Or in Calc 1, to give you the acceleration function of only one variable, then you integrate to get the velocity, integrate again to get the position function, right? So you start with position function, first derivative is velocity, second derivative is acceleration. Now we're just going backwards. Same thing. Start with acceleration, integrate once, get velocity, integrate again, you get position. Okay, so here we go. Hope I don't get tangled up here. So the acceleration vector is 2, 0, 2t. Yes, they gave it as I, j, k. I read it like that. The other information they said v of 0 was 3i minus j, which I'm writing like that. And they said r of 0 was j plus k. I'm writing it like this, 0, 1, 1. All right, so here's the way you do it. Yeah, the language we would say is just we are integrating the function, but in the process of integrating, you're really doing 3 integrals. Okay, so v of t. What's the integral of 2? 2t plus c1. What's the integral of 0? A constant, c2. What's the integral of 2t? T squared plus c3. Now, they told us v of 0, okay, comes out to be 3, negative 1, 0. Okay, actually, this is not right. Oh yeah, it is right. Okay, v of 0, that means I plug in 0. Put a 0 there, c1. There's nothing to plug in there. Put a 0 there, it's c3. Right? So this is v of t. That's true for any t. If it's true for any t, then it's got to be true for 0. So I plug in 0, that's c1. Nothing to plug in there, c2, c3. And it has to equal the velocity vector at 0, 3, negative 1, 0. That tells me that c1 is 3, c2 is negative 1, c3 is 0 right here. Okay, so I substitute these 3 guys right there, and right there. So that means we now have 2t plus 3, negative 1, and t squared plus nothing. Okay, so from here to here, I plug in c1 is 3. From here to here, c2 is negative 1. And from here to here, c3 is 0. Okay, so that's my velocity vector. And now I integrate again to find r of t, right? So I integrate this. So integral of 2t plus 3 is t squared plus 3t plus c4. And we got a lot of constants. You can't just keep writing c. The c's all can be different. So you have to say c4, c5, c6. Okay, integral of negative 1, negative t plus c5. Integral of t squared is 1/3 t cubed plus c6. Okay, and now they say r of 0. Let's see, r of 0 is 0, 1, 1. So when I plug in 0, I get 0, 1, 1. Okay, so put a 0 here and here, I get c4. Put a 0 here, c5. Put a 0 here, c6. and that has to equal 0, 1, 1. Okay, so that tells me C4, whoops, C4 is 0, C5 is 1, and C6 is 1. Okay, let's show what's happening here. All right. All right, so now all I do is put C4 is 0, so that's gone, t squared plus t plus 3t. Put a 1 there, negative t plus 1, and put a 1 there, 1/3 t cubed plus 1. So that's my final answer. Okay. So it's a lot of integrating, figuring out all the constants, C1, C2, 3, 4, 5, and 6. Okay. All right, then let's see. 19, can't see what time is it, about 6:45-ish? I think we're doing fine. 19. The position function is R of t is t squared 5t t squared minus 16t. When is the speed a minimum? Trying to minimize the speed for number 19. Okay. So by the way, remember we did some minimization problems in Calc 1, right? Maximize or minimize a quantity. So I come up with the expression for the speed, which is the magnitude of the velocity vector, right? So take the derivative. R prime is 2t, 5, 2t minus 16. The speed, magnitude of R prime, I'll call it f of t, is the square root of this thing squared plus this thing squared plus this thing squared. So that's 4t squared plus 25 plus 2t minus 16 quantity squared. Okay, so I'm trying to minimize this quantity. Okay, now, you may have seen this trick in Calc 1 also. The value of t that minimizes this is going to be the same t that minimizes the square of it. In other words, just take off the square root. Whatever t minimizes that is the same t that minimizes the square of that. So I'm just going to look at minimizing 4t squared plus 25 plus 2t minus 16 squared. Okay, remember that? Okay, so again, the t that minimizes this is also the t that minimizes the square of that. Okay, and we know this is a parabola which opens up. If I multiply it all out, it'll be a coefficient of t squared, which is positive, right? In fact, we know what it is. It'll be 4t squared plus 4t, 8t squared. Okay, that means it's a parabola opening up, which means just find the vertex. That'll minimize. Which means just take the derivative, set it equal to 0. Okay, so the derivative is 8t plus nothing plus chain root 2 times 2t minus 16 times 2. 8t plus, okay, that's 2 times 2 is 4. 4 times 2t is 8t. And then 2 times 2 is 4 times negative 16 is negative 64. So that means 16t minus 64 equals 0. So that tells me t is equal to 4. Okay, and I don't think they gave us any units, technically. If they did, we just give it seconds or whatever. It doesn't say. So if it doesn't say, we just leave it as t equals 4. All right, and let's see, just one more type of problem, the tangential and normal components of acceleration, 37 and 39. So I'll just do one of those and we're done. Then we'll break. I'll sneak in some of 14.1 during the second half, and then we'll take a quiz and then enjoy a nice 4-day weekend, right? For those of you who have classes Friday and Monday, that is. Okay, so 37 and 39, find the tangential and normal components of the acceleration vector. Okay, so there's only 2 problems with it. I'll just do one and you do the other one. So what you want to put on your cheat sheet is, sorry, I can see I'm getting more tangled up with all these wires and stuff. Okay, so 39. All right, so 875, equation 9, a sub t, tangential component of acceleration, r prime dot r double prime over speed, magnitude of r prime. 10, a sub n is r magnitude of r prime cross r double prime over magnitude of r prime. Okay, and this is a picture, but you don't really need the picture to do any of these problems. But this is what's happening in the physics standpoint. Here's the acceleration vector. Break it into its tangential components and normal components, because maybe you want to know how much is the tangential component. How much am I going this way? How much am I going this way? Okay. So I'll do 39, the harder one, and you do 37. For one thing, it's trig, and the other one, well, 37 is only 2D, right? It's only got I and J. 39 has I, J, and K, so I'll do 39. Okay, so R of t is cosine t, sine t, t. So by formula, you need the two derivatives. So first derivative, R prime. Derivative of cosine is negative sine. Derivative of sine is cosine. Derivative of t is 1. Second derivative, again, we will say we are taking the second derivative, but you open it up and you're really doing three derivatives, right? Three derivatives in one. Okay, derivative of negative sine is negative cosine. Derivative of cosine is negative sine. Derivative of 1 is 0. Okay. Take the dot product. R prime dot R double prime is that times that, two negatives, sine t cosine t, plus that times that, negative sine t cosine t, plus nothing, 0. That's nice. So this is 0, which incidentally, yes, it does mean that you might recall that means these two are perpendicular or orthogonal. Okay, two vectors are orthogonal or perpendicular if the dot product is 0. Okay, then the cross product, R prime cross R, that's a R double prime. So I, J, K, negative sine cosine 1, negative sine 0. So it's I times that minus that, so nothing minus a minus sign. Then J is the opposite of that times that, which is nothing, minus a minus cosine, so that's cosine. But because there's a J, there's a negative already there. Then K is that minus that, that's sine squared minus a minus cosine squared, sine squared plus cosine squared t, 1. Okay, then by formula, I need the magnitude of R prime cross R double prime. I need the magnitude of this vector. So it's a square root of this thing squared, sine squared t, plus the square root of this thing squared, cosine squared t, plus 1 squared is 1. Sine squared plus cosine squared is 1, 1 plus 1, so radical 2. And by formula, the only other thing I need is the magnitude of R prime. So R prime was way back over here. So I need the magnitude of this vector. Okay, so it's a square root of this thing squared plus this thing squared plus this thing squared. Okay, so square root of sine squared of t, right? Plus cosine squared of t plus 1. That looks like something we just did. Radical 2. All right, then just plug it in. So by formula, a sub t is R prime dot R double prime divided by magnitude of R prime. So the dot product was 0. Well, we already know 0 divided by anything is 0. A sub n was the magnitude of the cross product. So where was the magnitude of cross? Radical 2. Divided by magnitude of R prime, the speed, is also radical 2. So that very conveniently comes out to be 1. And there we go. Okay. All right. Do this without getting all tangled up. Okay, so it looks like if I use this headset, it'll be a lot better, I guess. I'm done with everything you need for the next test. 13.4. Okay, so you have until Tuesday the 23rd to prepare for all that. But I'll just get started with chapter 14 stuff, including right after today's break. So who knows, I might get up to 14.2 or 3 again. I'm trying to gain a day here, so it looks like I'll be able to do that. Okay. And so even on the day of the test, I'll let you ask questions if you have any. If not, we can just start the test earlier. And even next Thursday, the 18th, if you want to ask questions on chapter 13, that'll be fine. So coverage for the test is 13.1 to 13.4, and that's what you submit for homework. We did a huge chunk of that already in class, right? Okay, so it's almost 7. I get that. Let me check the chat. Okay, yeah, more things about microphone and all that. Okay, we'll see how that goes. Okay, yeah, I know there's a lot of stuff you can. I might have to try it later, but anyway, it seems like it's a little bit. So most of you have suggestions as to how to fix this, but anyway, we'll see how that goes. All right, so we will break. I will stop sharing right now temporarily. Let's see, how about 7:10? Break until 7:10. I'll put that in the chat also. Okay, I'll disappear and I'll also look at what you have in the chat too. Thank you. All right, folks, let's pick up where we were. I saw your suggestions, and thank you very much for all your suggestions. I'll try them out sometime over the weekend. I didn't feel like doing it now. I needed to focus on the math, I guess. But thank you. I'll try it all, and I absolutely know many of you are way better at, this kind of stuff than I am. And let me see if I can turn this thing down a little. Yeah. So anyway, okay. I will introduce 14.1. Anything I say from chapter 14 will not be on the next exam. Okay, I'll do some of 14.1. We'll take a quiz and then have a nice weekend. All right. All right, so what's chapter 14 about? The topic is partial derivatives. Okay. And by saying the word partial, it doesn't mean like half a derivative. It's a full derivative. So that's not the form of the word partial. Okay. Partial meaning there's a separate part to it. So it's not like a half a derivative when we say partial derivative. It's a full derivative, but there's more than one part, I guess is the way to say it. Okay, so we are now having functions of several variables, 14.1, page 888. Okay, and this is where we start to see the reason why we let z be the one that's going vertical, because we want z to be the height. Okay, we no longer want y to be the height, we want z to be the height. Okay, so we can have a function of two variables now. Okay, so a definition, a function of two variables is a rule that assigns to each ordered pair xy in a set D a unique real number denoted by f of xy. Okay, so this is the big difference. We're used to just saying f of a single variable, like f of x, or f of z, or g of y, or h of t, or something like that. But now it's a function of two variables, okay, which incidentally is the reason why Calc 3 is often called multivariable calculus, right? Okay, so in Calc 1 and even Calc 2, it was still pretty much a function of one variable, just f of x, g of y, h of t. But now you can have f of x, y, function of two variables. You can even have a function of three variables, f of x, y, z. You can have a function of four variables, f of x, y, z, t, where the coordinates are x coordinate, y coordinate, z coordinate, and time, for instance. Okay, so the domain and range, well, for a function of two variables, the domain is a subset of the xy plane, and the range is all real numbers, for instance. Okay, and what they're trying to show you here is you take a portion of the xy plane, let's say this is the domain, and all of these map to a value in z. You can think of it as the height. Okay, so if I'm on this point, there's a certain height. If I'm over here, there's a certain height. If I'm over here, there's a certain height, and this height might turn out to be negative. Okay. A way to think of it is in x and y, you know your usual xy coordinate system. Think back to Calc 1. I'll just make up something here. There's a function, right? Pass the vertical line test. So you give me an x, I can give you a corresponding y, right? That's true anywhere. 1x gives you 1y. Okay, so the input is a real number. The output is a real number. Think of it now as your input is something in the xy plane. So think of the plane of the floor. Okay, imagine if we were meeting face to face, I would literally point to the floor. But imagine you pick the floor. So the floor is the xy plane. Z equals 0, we said, right? So pick any point on the floor. There, 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 there. And all of those points have corresponding heights. So maybe I'm over here, the height is like that. And over there, I'm like that. And over there, it's way up here. And over there, it's 5 units below my floor, and so on. Okay. And it would also pass a vertical line test, so to speak, where if I pick any point on the XY plane, okay, and I go up like that, it's only going to touch 1 point. Okay, that's just like over here, right? In a function of one variable, you pick any value of x, it's going to touch at only 1 point. Okay, you pick a point in the x-axis. Well, now you're allowed to pick any point in the floor, xy plane, or I don't know, just take this paper. Okay, so imagine this paper. Take that point and that point, that point, that point, right? Various points. All of these have corresponding heights. Okay, and the vertical line test would be if I take any of these points and I go straight up and down, it's only going to touch at 1 point. It's not going to curl back on itself. So I don't know if you can see what I'm doing here. Take this paper and curl. So this would not be a function, right? If I draw a vertical line like this, it's going to touch at 2 points. That's just like, you know, go like that, right? So this is not a function, touches 2 points. Okay, so in space, if you're in the XY plane, okay, so if you have a 3-dimensional shape like this, right? It's going to fail the vertical line test. I can draw a vertical line which touches this funny shape in more than 1 point, in 2 points or more. Okay. So that's why we have z equals f of xy in general now. Okay, so you give me a point in the xy plane, plane of the floor, I come back with a different height. Okay, so that's what's happening right now. Here's some examples. F of xy. So that means in your expression, you don't have to have just one letter. You could have 2 letters. X plus y plus 1 over x minus 1. That's a rule involving x and y. F of xy is x ln y squared minus x, or whatever. So if I have this as the function f of xy, that means I need 2 inputs, like f of 3, 2. Right? So before, we were used to just saying, okay, f of 3, right? Or f of 2, or f of pi, or f of a million. Now you need 2 inputs, f of 3 and 2. So, okay, I plug in 3 for x, 2 for y, and so on. Okay, so there it is, radical 6 over 2. Okay, so that means for this function, whatever it looks like, on the point of the floor, 3, 2, right, on the xy plane, that's the height. I go up radical 6 over 2. And you give me a different point, I get, you know, a different height. Right? And of course, you could have a limited domain based on the function. Back over here. Whoops. Function of one variable, right? If you start off with something like this, first you think of all real numbers, right? So you start off with all real numbers. And then based on what you see, like square roots or fractions or ln's and so on, you might have a limited domain, right? Like for this, you know, okay, x has to be greater than or equal to 1. So you're only allowed to plug in stuff like that, right? You're not allowed to plug in 0. You're allowed to plug in 1, and you're allowed to plug in any number bigger than 1. So the domain would be bracket 1, infinity, right? A subset of all real numbers. So first you start off with all real numbers, but then you might have to throw stuff out based on the function, right? So same thing happens here. You might have a limited domain. You start off with all of R2. And if you hear me say R2, that's XY plane. If you hear me say R3, that's XYZ space, right? And you can even hear R1, but R1 is the same as R, the set of all real numbers, right? A real number line. Okay, R2 is like the XY plane. R3 is XYZ space. So f of xy, you start off with the entire XY plane, but you might have a limited domain based on whatever the function is. Okay, maybe there's a square root, or maybe you're not allowed to divide by 0 and so on. So you might have some very unusual subsets. Okay, that's just like what I had over here, right? You start with all real numbers, but then you might have to throw stuff out. So you start off with all of R2, which is the XY plane, and maybe you throw stuff out based on what you see. Okay. Okay, this table is an example of a function in 2 variables. It's called wind chill index. The 2 variables are along here, the actual temperature and the wind speed. Okay, so this is the temperature that you feel, wind chill index. Okay, so we know the temperature might actually be something, but because of the wind or the humidity or whatever, it feels like it's warmer or colder. Okay, so they have this here where it's a function of the actual temperature and the wind speed. So they have F of -550 equals -15. Okay, they make a little table there. -5 and 50 is -15. What they're saying is if the actual temperature is -5 degrees C, already cold, but the wind speed is 50 miles an hour, then it feels like it's -15 degrees, right? So that's a function of two variables, as it were. Okay, and you can see other examples that are here. Here's such a graph, good graph. So in this case, here's a domain. It's a subset of the XY plane. And they give us a first octant view, right? We like it. First octant, X, Y, and Z are all positive. And here's the corresponding graph. It passes the vertical line test. If I take any point in the domain and I go straight up, it's only going to touch at one point, right? And remember, I say up, it doesn't have to be up, it could be down, right? Part of the graph can go down. I mean, that's just like in one dimension, we say the Y value is how much you go up. Well, you might go down, right? You might have a negative value. So these Z values are definitely allowed to be negative. That would be like, you go below the floor, right? The height, quote unquote, is a negative value. So if I set the floor to be Z equals 0, and it's +1, +2, +3, right? Well, you can go down -1, -2. So they made it, quote unquote, nice here, where all the heights are positive, but you could have the heights being negative also. So that would be the graph. Okay. Am I going to make you do any of these graphs? Only very, very easy ones. Okay. Example is this. Right. We've seen this before, right? Just take the X, Y, and Z intercepts, right? And you can draw yourself a triangle. 2, 0, 0, 0, 3, 0, 0, 0, 6. Okay, that's the function f of x, y, example 5. F of x, y is 6 minus 3x minus 2y. Okay, now just like whenever you see f of x, you called it y before, right? In 2 dimensions. In Calc 1 and Calc 2, we always said y equals f of x, right? It's the height. So f of x, y is now going to be z. Okay, so you can always replace this with z. So just like f of x is y, f of x, y is z. And that gives us the height, which is the reason why we want z to be vertical. So notice if you replace this with z and do a little bit of simple algebra, it's 3x plus 2y plus z equals 6. We saw something like this before, right? Which has x-intercept 2, 0, 0, y-intercept 0, 3, 0, z-intercept 0, 0, 6. Okay, and you remember what's the root for the x-intercept? X-intercept means y and z are 0. So just put a 0 there and a 0 there. 3x equals 6, x equals 2, right? Likewise, for the y-intercept, you said x and z equal to 0. 2y equals 6, y equals 3, 0, 3, 0. For z-intercept, x and y are 0, z equals 6. So there's a picture of the plane. I know you don't really see the entire plane. It's kind of hard to draw the whole plane, but you can kind of visualize a triangle, right? So just take that triangle in space and just, extend it out. And you kind of get the plane. Okay, we might have to draw something like this from time to time. That looks like a hemisphere, right? Half of a sphere, upper half. So g of xy is square root of 9 minus x squared minus z squared, okay, which means z would be positive or non-negative, strictly speaking. Okay, if you do a little bit of algebra, this would be x squared plus y squared plus z squared equals 9. That's a sphere, center of the origin of radius 3. Okay, and then if you just do what they have there, z can't be negative, so you just have the top part. And you can see if I just have the top part, that is a function. Okay, your domain would be the circle, x squared plus y squared equals 9. Pick any point on that circle or in the interior, go straight up. It's only going to touch at one point. It's completely analogous, exactly analogous to this, is it not? In 2 dimensions, y equals radical 1 minus x squared. Okay, you're only allowed to pick something between -1 and 1, and there's only going to touch 1 point. Just extend it 1 more dimension, and you have this. Pick any point on the circle, x squared plus y squared equals 1, and go straight up, it's only going to touch 1 point. Right? Now, if you complete the entire sphere, right, if you have the entire sphere, then it's no longer a function. Just like if I complete this circle, right, completely analogous. Okay, now it's no longer a function. No, now it no longer passes the vertical line test, right? So again, a lot of 3-dimensional stuff, we just take the analogy of what do we do in 2 dimensions and kind of do the same thing. Okay. Okay, level curves, I think I'll hold off on that until next time. Let me try to show you a little bit of what's happening in the homework. Okay, I won't go too much longer. Yeah, these are obviously computer generated, some real nice pictures. Unless you're a good artist, some of you may be good artists, I'm certainly not. You have some pretty nice computer generated pictures there. And what's all this stuff? I'll talk about that next time maybe, but these are level curves. You just take a 2-dimensional object, and we can all draw stuff in 2 dimensions, and then you just tell what the various heights are. Okay. Here's an example of a level curve. This is supposed to translate to the 3-dimensional picture. Okay, it's like a contour map. You can imagine, okay, here the height is 0, then the height is 1, then the height is 2, and here's the top of the mountain, king of the hill for somebody. It's the very top. Okay, I guess that wouldn't be this picture here, but it'd be the upside down of that picture. That's that. Okay, get you started on a little bit of this, not too much, and then I'll give you a quiz and then we'll call it a day. Okay, so 14.1, again, take the notes, but this will not be on the next test. This will be in the test after that. So 1, 3, 9, and 25, blah, 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 blah. Let's see what we can do. Okay, number 1. Consider the function W equals f of TV. W is the wind chill index. T is the actual temperature. V is the wind speed. Numerical representation is given in table 1 on page 889. Okay, so that's the one that we just looked at, right? So unfortunately, in order to do this problem, you have to keep bouncing back and forth from this table. A, what is the value of f of -1540? What is its meaning? So we just look it up. -1540. -1540 is right over here. Where is it? -27. Okay. What does it mean? When the actual temperature is -15 degrees Celsius and the wind is 40 kilometers per hour, it feels like it's -27 degrees C. That's all. Right? Function of 2 variables. B, describe in words what the meaning of the question, for what value of V is f of -20, V is equal to -30, then answer the question. Okay, so this time we have a constant, -20. That's the temperature. So when the temperature is -20, at what velocity will it feel like the temperature is actually -30? So here's what I have. When T is -20 degrees C, at what wind speed will it feel like -30 degrees? Okay, and I have 20 kph, 20 kilometers per hour. Let's see how that's borne out in the table. Okay, so it says that T is -20. So I only look across this. Okay, so only look across this row, and then they say, where is they're a -30 entry. So -30 is right there. And what's the speed? 20 kilometers per hour. Right? Get the idea? That's all. So you can hold one of the variables constant. I never like it when they make you turn back and forth. You know, the questions on one page and then the pictures on the other. Where am I? C, describe in words the meaning of for what value of t is t comma 20 equal to -49. So 20 is the wind speed. So at what temperature with a wind speed of 20 kilometers per hour will it feel like -49? Right? At what temperature will a 20 kilometer per hour wind feel like -49 degrees? Okay, the answer is -35 because so the wind was 20 kilometers per hour, right? So you only look down this column. And where in the column is there a -49? Right here. So that's -35 degrees. Okay. All right. It's not that bad, right? D, what is the meaning of the function W equals f of -5v? Well, that means you're constantly at -5 degrees. Okay, so at a temperature of -5 degrees, okay, you're changing the wind speed and what will be the apparent temperature, right? So f of -5v at a temperature of -5 degrees, what will the temperature feel like at a wind of v kilometers per hour? And then E. What is the meaning of the function W equals f of t 50? 50 kilometers per hour, right? So what will the temperature feel like at a temperature T and the wind of 50 kilometers per hour? That's all. Okay, I'll hold that a little longer for you. All right, what time is it? Okay, about 7:35. Okay. Start you off with a little bit of stuff here. All right, so that was 1. And I'll let you try 3 on your own, I think. Okay, so let's jump to some of this stuff. Okay, 9 is a function of 2 variables. 11 is a function of 3 variables. So let me do 11, which I think is not that bad. F of x, y, z. So if you have f of x, y, your domain is a subset of R2. The biggest possible domain is all of the xy plane. That's just like in function of 1 variable. The biggest domain is all real numbers. 2 space, the biggest domain is all of R2, the xy plane. 3 variables, the biggest domain is all of xyz space. Take a point in space. Okay, so 11. F of x, y, z is radical x plus radical y plus radical z plus ln 4 minus x squared minus y squared minus z squared. Okay, and evaluate blah, 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 blah. Okay. Here's the function. Find f of 1, 1, 1. Okay, so you have a function of more than 1 variable. We're used to f of x. But now you can have f of x, y, or even f of x, y, z. So just plug in 1 for x, y, and z. Put a 1 there, 1 there, 1 there. So radical 1 plus radical 1 plus radical 1 plus ln 4 minus 1 minus 1. That's ln 1. ln is 1 is 0, so that's just 3. Okay, they asked you to describe the domain. Okay, x has to be greater than or equal to 0. Y has to be greater than or equal to 0. Z has to be greater than or equal to 0. Okay. Now, ln, we know we can only take the ln of positive quantities, which means this expression, 4 minus x squared minus y squared minus z squared, has to be greater than 0. If I throw x, y, and z over to the other side, it says x squared plus y squared plus z squared is less than 4. Okay. Now, x squared plus y squared plus z squared equals 4 is a sphere, center of the origin, with a radius of 2. Okay. And this tells me I'm in the first octave. So I want the part of the sphere, center of the origin, radius of 2 in the first octave, not including r equals 2. So imagine you have a sphere, radius of 2. Okay. You're only in the first octave, and you're not on the sphere itself. So it's sort of like a dotted sphere. You know how we had solid and dotted lines? Okay. So we drew stuff like that, right? Means you're not counting the circle itself. If I go like this, I'm counting the circle. So maybe I want to talk about the interior. This says the interior and the boundary. This is the interior, but not the boundary. That's sort of what you have here. If you can imagine a dotted sphere, which is kind of hard to graph, but that's the concept. Okay, so it's a part of the sphere, center of the origin, radius of 2 in the first octave, but not including r equals 2. Okay, I'll do a couple of domain problems and then I'll stop. And we have plenty of time to do the quiz and then quit. Find and sketch the domain of the function. Okay, now it's not so bad as you might think. We're not sketching the function. We're sketching the domain of the function. So if it's in x and y, it's just going to be a subset of x and y. The only exception to that is 21, okay, which is a subset of R3. Okay, all the ones from 13 to 20, okay, again, notice you're not sketching the function, you're just sketching the domain of the function. It's a subset of the XY plane. And we've been doing XY plane drawings quite a bit. Okay. All right, so do a couple and then I'll stop. Okay, 13. F of xy is radical x minus 2 plus radical y plus y minus 1. Okay, this tells me x is greater than or equal to 2. This tells me y is greater than or equal to 1, right? So here we go. Here's x equals 2. Here's y equals 1. And here's the region where x is greater than 2 and y is also greater than 1. So this is my domain. It's a subset of all of R2. You start with all of R2, but the only part that you actually have is this, including the boundaries. So it's here and here. So if you can imagine just this portion of the XY plane, that's where there are Z values. So right in here, there's different heights. Okay, and yeah, in this case, they're all positive or non-negative, strictly speaking, right? So only here, there's a height, and over here, there's a height, and over here, there's a height. But over here or here, there's no graph. There's no Z value up there. There's a Z value here and here and here. They're up somewhere. Okay. In fact, the Z value right there is 0. If you plug in 2 and 1, that's 0 plus 0, 0. But over here somewhere is the point, I don't know, 10 comma 20, right? What's the height? Plug in 10, plug in 20, and you get a corresponding height. Okay, and then I'll do 17, and I think I'll stop. G of xy is x minus y over x plus y. Okay, so because there's a fraction, I know I can't let the denominator be 0. So when is the denominator equal to 0? When y is equal to negative x, right? If x and y are opposites, I would get 0. So y is not equal to negative x. So the domain is everything besides the line y equals negative x. So I draw a dotted line on y equals negative x. That's kind of like, you know, on a number line. On a number line, you would punch out a hole, right? You know, for some reason, you exclude a point, right? Shade all of this, shade all of this, but there's a hole right there. That's kind of the same thing here, right? Where the only thing I'm doing is I've got all of R2 and I just kind of get a scissors and cut out y equals negative x. And then I shade all of this. So there are heights everywhere here. There's heights everywhere here. There's no height at the origin, no height at 1, -1, 2, -2, -2, 2, negative a million, million, pi, comma, negative pi. There's no heights there, but everywhere else there's a height. There's a z value, and I can just plug in for that. Okay. All right, and I think I'm done, folks. Okay, and let me check the chat real quickly. That, thank you. Okay. Yes, I see a lot of you gave me good things, and I'll try it out over the weekend. But yeah. Okay. And yes, you can get a lot of good visuals on 3D space, but we don't really want to spend too much time on that. I want you to be able to do the math that's here too. So thank you for all of your suggestions, and thank you to everybody who gave me this. If you were part of it, if you have no idea what I'm talking about, don't worry about it, I guess. But thank you so much. I appreciate it very much. And it helps all of us, I guess, helps all of you too. Okay, any other questions? Otherwise, we'll go to the quiz and then we have a good weekend. Okay, so quiz time, get your cell phones out or be able to do a screenshot. As usual, put your first and last name and first and last name of everybody in your group. I'll raise it up there. Okay, so take a picture. I'll hold it for maybe half a minute. Okay, you got a position vector. R of t is t over t squared plus 1, radical t plus 3, ln t. It's almost like you're just reviewing some derivatives. Okay, question 1. Find r of 1, position vector. Find r prime of 1. So you have to find a derivative, plug in 1. Then 3, find t of 1, the unit tangent vector at t equals 1. So you can get the answer to 3 by taking the answer to 2 and just divide it by its magnitude, right? I'm practically telling you what to do. Okay, so number 1, r, we'll just plug in 1. Your answer should be a vector, by the way. Let's see, all 3 of them should be vectors. Number 2, find the derivative. I guess you have to remember the quotient rule, right? How do you differentiate a square root? ln, you should all remember. And then plug in 1. And then 3, find capital T of 1, the unit tangent vector, which means just change number 2 by dividing by its magnitude. Okay, I will now assume that you all have it. So go ahead and get started. Let me get this set up. I'm going to take this off now because okay, so I'll set up your breakout rooms.
Okay, I unplugged the thing, so I'm back to speaking over the air, but I think that's okay.